Well, I guess it's 7 o'clock, and I'm going to get ready to start here. So we're going to cover, I've got a lot of ground to cover, so I don't want to take too much time here, but I'm going to give a few minutes for people to come in. So I have a microphone that was supposed to be here on Monday that will be better, hopefully, than this one, that will be able to cut out the keyboard strokes. But it is not here yet. So there's some problem with the shipping. Imagine that. I'm sure many of you have had some of the similar problems with shipping in the last year or so. So we'll see how this goes. We'll continue to try to get a little better every single time. Just like I'm going to try to get better just a little bit every single time, and hopefully you guys are also attempting to get better a little bit every single day. So this is all we can hope for. All right, so all right, let me point out that I put an end date of tomorrow on the survey, and so if you haven't done that yet, go ahead and peek in on that survey and get that done. And if you don't want to do it, that's perfectly fine. It's not a problem. It's anonymous, so I don't see your personal results. I see everyone in the class combined. So I don't need to know what you think of your programming ability, but I want to know what everyone in the class kind of evaluates themselves. Okay, so yeah, I'm just going to get started here. I'm going to be typing away, at least to start with. So one of the things that we have to do in computer science, anytime we're understanding a very complex system, is abstraction. And I think I talked about that a little bit on the first day. And so I'm going to talk a little bit about how we can abstract a little bit to give us a better sense of kind of how to handle different things in the computer. So this is one way to do a computer level hierarchy. It's not necessarily super important, but it allows us to be able to talk about which layer. They're not always formal, but we can talk about then which layer or which level are we're abstracting at. So the very top level here is the user level. And the user level is the level that you're used to. Oh, actually, I should share that screen. There we go. So it's the user level, and that's what you're used to. So we can think about any kind of executable program. So any of the programs that you're using. So an example, I suppose, would be Chrome, right? That's an example of a program that's being run. Another one might be Word, right? So these are programs that run on your computer or on your phone. Right, because in this case I'm going to talk about PCs, and most of the time that's where I'll be centered, but certainly applies to other places as well. All right, so then the next one we have is high level languages. And here we would see Python. We would say C++, Java, anything that we can write computer commands in. Now, so let me talk a little bit then about why we have these two different levels. Because Chrome, let's say just an example, Chrome is written in a high-level language so that anybody who's coding that goes to the high-level language and that's how they program it. but then it has to be compiled. Even Python, although it's an interpreted language, in order to create an executable file, we have to do this transition. Python does it live. It's a completely different story. But so we have to create this. Wait, I'm sorry. I should back that up. Usually it does it live, but it doesn't have to do it that way. You can create executable files from Python. So what it does is it creates this executable file so I don't have to see or look at the code in order to be able to run it. So I can use the computer and not have any idea about how to program a computer. In fact, the vast majority of people who use computers don't have any idea how they work internally or anything. They don't have any idea of how to program them. So now we have to have something that translates from one to the other. In this case, it will be some kind of a compiler or something that changes from the high-level language into the executable files or into something that the user can use or look at. So that is needed. There'll be transitions all the way along down through here. We won't necessarily talk about what they are and how they work necessarily, but they do exist. Okay. Assembly language. So this is assembly code. And in fact, actually, yeah, Maria this is the language we'll be using. So that's an actual example of that. Another one would be MIPS. There's plenty of other examples out there. But see, the computer can't understand high-level languages. It has to translate it into something lower level in order to actually run, because in the CPU, it doesn't know what an if statement is. It has no idea. So that's why we need something to bring it down closer to. And so we translate that. It takes that thing and it translates it into an assembly language. If any of you have ever used C, not C++, but C, and had a compiler system that's a two-part compiler system, it actually translates into an assembly language, and then it does it again into something called machine code. And we'll get to that one in a second. So system software is our next level. This is our operating systems. Operating systems. And the library code. So library code would be it's code that the computer uses. So if you've ever seen a file called a DLL, that would be a library code. Digital library something. I'm sure what DLL stands for, something like that. So it allows it to be written in a different form than is even readable by humans. Assembly language is still readable by humans, although it can be difficult to read, but you can learn how to do it. The system software, operating system, that stuff is not readable by humans. Generally speaking, it's created at a higher level, either at the high-level language or at assembly language, and then it's compiled or mashed together and into an operating system, into the system software system. So some of the examples, right, might be like the driver for your monitor, or for your graphics card, or for your mouse. Any of that kind of stuff also would be on the system software level. All right, so then we have the machine level, and this is instruction set architecture, or ISA, and this would be, this is at this level, it's all electronic. and so we would represent it in ones and zeros, at least on most computers. But in this class, for this class, we'll do it in ones and zeros. All right. So, and there's really not any good examples there. And then the next one is control. And control is microcode and hardwiring. So it could be a microcode or part of an instruction, or even actually a complete instruction. It's possible in some systems to do that. And then, but also we can have hardwiring, and I'll explain what that means, what the difference between those two, actually towards the end of the lecture. But you'll understand a little bit better. So this is actually on the wiring, at least some parts of it here. Because remember, we talked about this last time, at least briefly, is that if I can do it with hardware, I can do it with software. And if I can do it with software, I can do it with hardware. Which means that these microcodes, although they're very close to the very, very basic level of the electronics, they're not, right, it's actually interpreting the ones and zeros. And, but I can actually hardwire that so it doesn't have to do that. And so, and what that does is it helps speed things up, because we don't have to interpret what we're going to do. We can just do the same thing on a bunch of different things. Actually, a great example of that is encryption. You can buy a piece of hardware that will just encrypt all of your data that's going across the network. As long as the other person knows what product that you're using, then they can go the opposite direction, right? So they can decrypt it. So then the next one is the digital logic level. This is circuits, gates, and both the circuits and the gates we will be studying in this class on some level. We're going to look at actually how things can be wired on a real simple level to add two binary numbers together, because we can do all of that with electronics. And it turns out that we only really need to look at one digit, because we just repeat that across all digits. So, all right. So that's a little bit about hierarchy. And again, like I said, we abstract, right, a lot of this. This just helps us with abstraction, right? So like, there isn't necessarily something to translate between the two of these, but we use the control level to abstract for a human, so we can actually understand some of the microcode stuff. Now, I don't know why anyone would ever want to do that, but people who are designing the circuits and the gates certainly do. So otherwise, and then, like I said, we will go and look at some of the circuits and gates, and we'll look at how they work and how the electronics actually flow, at least briefly. Okay, so let me come down here and go down to the next one here. Cloud computing. So the first thing to think of here when we think about cloud computing is virtual machines. So a virtual machine is a machine that is used on the computer, right? It's not, so you don't have physical use of it. So it's an internet. Oh, I need to change the size of that. Service. Service that simulates some part of a computer. That's just a good general way. It's probably not a super technical version of that, but that's good enough for us. All right, so let me look. There's three main categories. There's SaaS, and that is software as a service. An example of that, Square. I think most of you have either used or are familiar with that, right? That's purchasing and or selling. So retail helps the retailers. So this is something that I don't have the programmer working on my computer for Square. I have some portion of it that I can then interact with the service. So I have a small little program, but it allows most of the computing to be done on some database somewhere. Another one is Google Drive, or any of the Google services actually. So Google Apps. So if you did Google Sheets or Google, what is the word processing one, whatever it is, those are free services that are out there. Free is probably, it's kind of loaded. It doesn't cost you any money. It does cost you in privacy, but you get to make your decision on how private you want to be. So it's becoming more and more difficult to become private or to stay private. So right, okay. So those are a couple examples. There's hundreds and hundreds of more examples out there of software as a service. So basically, instead of running the program on your computer, you run the computer on some server somewhere on the internet. Yeah. IaaS, infrastructure as a service. Oh, imagine that, huh? So one of these is Dropbox. Right, so for those of you who aren't familiar, Dropbox is a storage. So basically you can put files and pictures and whatever you want onto external storage. So it's storage that's not on your computer. And that works. Another one is Microsoft Azure. Microsoft Azure is it provides processing power from Microsoft. Microsoft provides processing power for people to use. So and then the next one is PaaS, or Platform as a Service. Big surprise there. Oh, actually that should be a capital S on that. And this one would be Google App Engine. Another one is Citrix. So what you do here is you actually create a system. So it's as if it's a computer. It looks like a computer. It acts like a computer. It thinks it has a certain number of monitors. It thinks it has a certain amount of RAM, a certain amount of processing speed, everything. So all of that is handled externally on the internet somewheres in the cloud. And then also there are serverless computing options. So all of these other ones would be on a server somewheres. There are some serverless computing options. So some of that's some of the peer-to-peer networks. One of the ones that's kind of a buzzword is Hadoop, but that's just one of them. But so the serverless. Oh yes, yeah. Why? Yeah, it's all good. All right, so yeah, peer-to-peer stuff. Okay, so one of the things that the cloud computing does for us that's actually can be really, really useful is, let's say I have a Dropbox and I'm storing a bunch of pictures because I'm, going out and taking wildlife pictures or something like that. Who knows? Right? Whatever it is. Or I'm taking pictures of all the activities that I do. Right? So, so I have this Dropbox for that, and I can get one for free. It's a certain size. I'm not exactly sure what the size is for the free version, but it gets full. What I can do is I can go to Dropbox and I can actually pay them by the month to increase that storage. So I have more storage available to me as a user. And they're able to just expand it for me seamlessly. And the same thing would happen with Square, although Square generally doesn't scale necessarily. But let's say you had a single business, all right, and you were using Square, and then you switch to 2 locations, or maybe you have a storefront and a food cart, or some kind of a mobile service that you can use, and Square just goes right with you. The same with Google Drive, right? You could have 2 computers or 5 computers or 10 computers, and it just scales. The same thing with, say, like Citrix. If you have a certain configuration for this computer that's being used by somebody, and then they need to make a bigger hard drive. They need to have a bigger hard drive, or they need to have more memory or more CPU power. You can just do that right in line. You don't have to change any. You can change those settings automatically without having to bring down. Well, you have to bring it down, but you don't have to. You can reboot it again because, like I said, it works exactly like a regular computer. It's actually pretty neat to use those. Okay, so let me bring this down just a hair and bring some of these down as well. Okay, so fragility of the internet. This is a really interesting topic. Let me give it some more space here. I'm going to just move these way down and give myself some more space. Okay, so that's still not enough space. Come on, keep going down. There we go. That should be enough. All right, so I'm going to use the draw function here and see what we can do. Okay, so let's assume, so in the early days of the internet, remember what they were using it for? I talked about this last time. The people who were in the internet or using the internet were military contracts. There were people that were doing work for the government. And so let's say, we've got a network, and we've got this right here, and this is LA, right? So like UCLA is down there, or USC, I think. I think they're both in that city. So then we've got, let's say we've got up here, we get, Seattle. And then we've got Minneapolis. Just going to put M in here. That'll be good enough. And then I got over here, got New York City. Oh, we can't forget here, about halfway between these two, we've got Palo Alto. Which, by the way, part of the reason why they put it there was because it was close to Stanford. So Stanford is maybe there. And then down here, we say we've got, I don't know, USC. Not, is it U? No. Say FSU. So Florida State University. I don't know why. I had USC on my radar here. And then maybe we've got up here, we've got Harvard. Let's just, let this is enough to kind of, Harvard. These are some of the important places. Not all of them are important. But let's say, right, these two are connected here. And there's a direct line between these. Go in there. There we go. And then maybe like this. These lines could be really expensive. Okay, so okay, now remember this was done for military purposes. Then they kind of came up with the idea for the internet, and it was done in the 60s, in the 1960s in the United States. Well, what were they really scared about or really worried about in the military in the 1960s? Well, that was nuclear strikes because the Cold War was going on. And so they were serious about these things, and they did design the network to withstand a nuclear blast. And so this actually is not how the network would work, because a prime target might actually be New York City. So what happens if I come in here and I wipe out New York City? And all of those lines are now broken. Well, New York City's gone, right? It's been nuked, and its network is destroyed. But Harvard, let's say, still exists. Well, Harvard's now disconnected from the network, so Harvard wouldn't be able to communicate any longer. So this would not be a very good system. And so that's why they designed the computer system. That's why it's called the World Wide Web, because every single place that's connected is connected many different ways to the internet. It's not everyone, right? Because all the areas, the different areas are connected on these trunk lines that go around the country and around the world. In fact, actually, I just put in the United States, I guess, to illustrate a little bit. But then this has been extended to the world as well. And so if you want to send an email to Dubai, you would, it might go through Florida, it might go through New York, it might go through California, it might go through Brazil. We don't know, because what it does is it picks, the idea is for it to pick the path of least resistance to get there. And so it might go through France, it might go through Morocco. We don't exactly know for sure how it will go. There's some really neat services. You can go out there and actually see how things move through the network, and you can study that more in a networking class. It's actually quite fascinating. But they knew that the internet was quite fragile, at least to start with. But now there's a new problem for the fragility of the internet. Because the internet has millions of connections or millions of different nodes, sites that can be connected, and millions of different lines, tens of millions maybe, connections between 2 points. And so it would be difficult to take down the whole internet with nuclear weapons. It would be very difficult. But what you can do is you can create cyber attacks. And so cyber attacks might be able to flood the network with so much either traffic or so much garbage, or just specifically attack the nodes to take down different areas. And so in this case, you have the same effect as far as the network goes. And with everything relying on the network more and more, this becomes more and more of a danger. Not just necessarily in times of war, but also in times of peace, because we at least heard some things about network attacks being used between countries. I mean, kind of, but different attackers have been attributed to different countries. So this does happen, and we know it happens, but it's certainly something that is more of a problem, because when somebody creates this cyber attack, the program that does the attack can replicate itself. It can create millions and millions and millions of copies of itself. And in fact, we've seen some really nasty viruses or other kinds of malware that have gotten out into the world and actually have brought down networks for a short amount of time. And one of the things I've talked about is the power network being particularly vulnerable, and it is particularly vulnerable because my desktop wouldn't work if there was no power. My laptop would only work for a few hours, and it brings down everything. I mean, there's a lot of things that could still run, right? Your car could still run until you ran out of gas, because all of the pumps everywheres are digital. And there's no power to them. You can't run them. So what do you do, right? So, and it's the same across lots and lots and lots of different things. So we rely on power a great deal. Okay. Want that, I want that. Okay. All right. So let's grab this and give myself some more room again. Oh, I should talk a minute about the thumbnail picture that was on for the stream, and that is a picture of why am I completely drawing a blank? His first name. Von Neumann. Why can I not remember his first name? Okay, internet time. Von Neumann. John von Neumann. So he came to the United States, it looks like. I think he came to the United States during World War II. Anyways. Oh, no. Yeah. So he actually worked in Germany. Okay, well, there we go. So John von Neumann. All right, so this is named after John von Neumann, who is the one who came up with this, by the way. Some people say that, or they'll talk about him being one of the most brilliant mathematicians / computer scientists of all time. That very well might be. There's a lot of very good ones, though, so it's hard to know. So, and that have made major contributions. All right, so there's three main things that are part of a von Neumann architecture. There's three defining characteristics. It has three parts. Has three parts or three structures. These are hardware structures, and let me go over them. The first one is the CPU. The CPU consists of an ALU, or arithmetic logic unit, and a control unit. And we talked about those some before, and we will talk about a little bit more here in a minute. Okay, the next one is there's memory. Oh, I'm sorry. There's one more thing in here. Registers. Memory, and we can think of that as RAM. And then it also has an I/O system, input-output system. Those are all required for a Von Neumann system. Okay. The next thing it needs to have is sequential instruction processing. So you can think of that like a recipe, right? We do the first thing, then we do the second thing, then we do the third thing, then we do the fourth thing. So we're just going to do them one by one right in a row. So that's sequential, in order, instruction processing. So we're going to process the instructions in a specific order. And when you look at something like Python, that's what Python does, right? So Python starts at the top and it just works its way down. Now sometimes you'll use like some kind of a loop system or some kind of an if statement that will allow you to kind of bounce around. Actually, ifs don't let you bounce around. It lets you skip things. But a loop or some kind of a class system would let you jump to a different place. But those, we can just think of like when a for loop gets to the bottom, or when some kind of a loop gets to the bottom, it just says go back to the top again. And so it really is still sequential. It does one instruction at a time, one after the other. Single path between main memory and the CPU. This is actually pretty important. And I'll talk about what those look like, how those paths work. This is only partially true. Well, no, that's not true. There's only one way to get from the CPU to the memory, and one way to get from the memory back to the CPU. So we could have two different ways, but they're directional, right? So it's like one-way lanes. We can think about it that way. No, I don't want that. I want to break from this. Those are our three things. Let's go back up to 22 here. So now there's four different ideas. So in a Von Neumann system, because it's sequential instruction processing, so I'm going to look at what an instruction, how to get through an instruction. So let's put it in the same structure. Oh, I did not want to do that. No, that's all right. We'll do this. It's there. Yeah, there we go. So I'm going to call this instruction operations, and these need to get done in order. So that's another very, very important thing, is that these get done in order. So the first thing that happens is we fetch. So what we do is we get an instruction from memory. And again, I need to push these down and get them out of the way. Keep using up all the real estate. All right, so the first thing is to fetch, and the second thing is to decode. And in decoding, we decide the control unit decides which part of the ALU will be used. The next one is to load, and we will load operands from the memory. So every single instruction has two parts to it. And there are exceptions to this, but we'll just consider it this way to start with. There are two parts. There's the operator and the operand. So the operator is what you're going to do. So like if I want to add, then I will use the command for adding in the operator, and then the operand is the thing I want to add. And curiously enough, we don't actually add values, we add memory locations. So what it will do is it will go out to memory to get the information that needs to be added, and then it will actually do the adding. And that's how it works. Okay, so then the last one here is execute, or we could say execute and store. So then what it does, in this case actually, it's going to do the operation itself, and then so do the operation and store the result in memory. Some more space in. Come on now. All right. The book has a really nice picture, I think. So let's use black again. So where are we at for time? Okay. So this is a CPU. This box represents the CPU. This is memory. And this is the I/O system. Okay, so what we do in a von Neumann system, because remember, we have a way to send things back and forth. We have this thing called a bus. This carries information between places. And so when it talks about fetching an instruction from memory, then that comes out of here, goes down onto the bus, then goes down, and then it comes out from here into there. And then we decode it internally, and then we're going to load operands from memory. So it sends out a request from memory to get some operands. It goes over here, and it sends the request in. The request is returned back down this line, and we go over here, and it comes back in on the CPU. And then we execute, so we're going to do something internally here, and then we're going to store this back in memory, so it's going to go back out here and down and out. And so there's some things that will be shortcutted by this a little bit, because sometimes we actually will display it on the screen, and so that would require us to go back out here. So, but there's a way to kind of shortcut this a little bit. I'm going to delete this. I'm going to delete this and this, because some computers, they don't just use a bus, they use a data bus. data bus. And we're going to go ahead and do the lines like this on the data bus. We can also get data from the I/O, and we can send data to the I/O, right? So like if we want to print something on the screen, then it goes to the I/O. All right, so now I'm going to use a different color here. This signifies the address bus. When it says data, that really means the operand. Okay, so the thing we're going to add or subtract or whatever it is. Not the thing, sorry, the address of. Well, that's not completely true. It's the thing. Actually, it is the thing. All right, so, but here's the deal with this is that in this case, the CPU sends out an address and it goes to memory. Or it goes to the I/O device. All right. Oh, hey, look at that. That helps. All right. I'll bring these down again. I won't need to go that far. So let's go to a third color here. And our third color is our control. And the control not sure green and red were a great combination. I'll quit using green in the future. That control is the whole operation together. So that's to tell the information right to the CPU what's going on, and yeah. So that control, so information or data can be sent to that as well. So I think that's a good picture personally. Well, it's cutting part of that off, isn't it? All right. Well, need to figure out where's it cutting off. Right there. Okay. All right. That's control. And this is the address bus, the red one. Okay. That's a little bit about the von Neumann system. We're going to study the von Neumann system almost exclusively. That's just what we're going to work on. And the reason we're going to do that is because any of the other systems are different, and we can talk about what's different about them that makes them different. Okay, so then we get to non-von Neumann systems here. These are usually special purpose computers. Again, if I had an embedded system, right? So like the computer that's in your microwave, right? That could be a non-von Neumann system because it wouldn't need the same kind of general purpose that the other ones have. So these are usually special purpose machines. Although there's a possibility that we'll go away from the von Neumann system soon, but all the computers have been using a von Neumann system since the very, very beginning. So we'll see how that we'll see how that goes in history if that continues or not. So now we have parallel processing. So the thing is, we have multi-core, multi-core processors. Well, how does that change things? Well, the answer is nothing, really. It doesn't really change things. The same thing is true here, except for there's just multiple CPUs hooked up. The memory system is the same and the I/O system is the same. Well, maybe. That's in a shared memory system. Or we can have a distributed memory system. In a shared memory system, there's only one memory. And the I/O is there's only one I/O, right? There's only one I/O system, right? You can have multiple mice, you can have multiple keyboards, but there's only one system for I/O. That's shared by all of the CPUs. When we say processor, we really mean, well, it gets complicated because there's exceptions to everything. But generally it means a whole CPU that's in the computer. And so in a distributed memory system, because remember, the farther away things are, the slower it is. So if we put a bunch of CPUs here, then that's going to be slow getting to the memory and back. So, but what we can do instead is we can combine the CPU and the memory together in a distributed system. So each CPU has one memory, or each memory has maybe one or two CPUs. You can think about it that way as well. So they kind of get nested into a smaller group, and then it only has to communicate with the I/O so it might have a different bus just to communicate with the I/O, maybe not. But internally it can communicate much faster because those things can be put close together. And then also we have two other subjects here, and that is multitasking. And multitasking is when there are multiple programs running at once. Just have that in, make it a little easier to see. No, I didn't want to do it that. No, that's weird. All right, so just make it lighter. Okay. I don't know how cell phones are working still today, but I'm pretty sure that this is still the case. So has anybody ever thought about this? On your laptop, you can put a program like OneNote or whatever, or your browser, and you can put it's in a window, right? You can have it in a window mode, and you can make it smaller than the screen. And that way you could have two of them on the same screen at the same time. This is great. This is really useful if you have a large monitor. But when you look at your cell phone, can you do that? The answer is no, you can't. And that's because on a cell phone, you're only allowed to have one active program at a time. And that's the program that's in front. It's very interesting. So it doesn't, well, potentially does do multitasking. But what happens is the program that's not in front gets paused, and you're not allowed to interact, and it doesn't do anything. Now, this isn't 100% true because the clock continues to still tick, even though you're not looking at the clock. And it might still update your messages, or update. Right, so you might get a new message, or some new message from a friend, from an app or something like that, but it doesn't display on the screen. But it has downloaded it and put it on your onto your phone. So this would be an example of multitasking. Sometimes it switches from the main task. It does this very, very quickly, and you don't even notice that it did it. But it can do it quickly and then jump back and forth between them, and it can do it silently. So the other one is multi-threading. And in order to be able to, so this, of course, is multiple threads in the processor. So what multi-threading does is it takes a large operation and it breaks it into smaller pieces, and then that way it can process each one individually, and then it kind of brings them all together at the end. So we can think of this, a good way to think about it is if you've ever studied merge sort. So this would be something that you would have hopefully learned in CS1. And in merge sort, right, it splits the list in half that it's going to sort. And so each one of those can be assigned to a different thread. And so it can run those threads in parallel until the two halves are done, and then it merges them together. This can help with the speed, especially since, right, we're in parallel processing. So if you're multitasking, you can have different CPUs doing different tasks. In fact, there'll be something that's controlling your multiple cores, or your different CPUs, that'll assign tasks. And it will assign tasks based on how busy they are. And then also with multi-threading, right, if I have a merge sort, in fact, when I used to teach CS2 in Java, I did a lab where the students did merge sort. And merge sort in Java will make use of multiple threads. And I showed them kind of how to do that, like how to make the language do that. It's really a neat thing. And then what they did is they timed it because they told it how many threads to use. So use 4 threads, use 8 threads, use 16 threads, use 32 threads, use 64 threads. And then I asked them to kind of look at how long it took, because we did some timing on things, and to see is the program running better when you increase the number of threads. And it turns out that threading is only helpful until you fill up all of your CPUs at the same time, and then it's not really useful at all, because it ends up actually switching between the threads quickly. That's kind of an interesting thing. So we will I don't know that we'll talk too much more about multiple threading. That's more of an operating system thing, or parallel processing and all. We're going to be talking about the single straight line stuff, and that's what we got here. Don't know if there's any questions. Looks like the number of people watching today is down quite a bit. That's okay. Everyone will get a chance to watch it over the weekend if they like. I will look to put up an assignment. It will be based on everything up to and including today, and then that assignment will go up. Hopefully in the next. I'm hoping to do it tomorrow evening, so that's my hope, but we'll see. And so it should be up. So when you get up Saturday morning, make sure you get a good night rest, and then get up Saturday morning. Then you can go ahead and start on it. Or you could wait until 30 minutes before it's due. It's up to you. I wouldn't suggest waiting till 30 minutes before it's due, because you'll it might take more than 30 minutes to complete the task. So, all right, that's all I have. I will also have a document up. I know there were some questions about assignments and kind of what I expected, but we'll work through it. This, by the way, for some of the things we do, we're going to you can certainly do something like this, right? If I ask you to draw a picture of something, maybe you would actually draw a picture very much similar to this. Just make sure you put it into a PDF. I'll put out a document for that. All right, I think that's all I have for tonight. So I'll wait a couple seconds here, and then if there are no questions, then we will close down and call it a week. We got through the first chapter. We only have 10 more chapters to go. So maybe we'll get done by Thanksgiving. We're not going to get done by Thanksgiving. So, but we will move along. If we notice on the schedule, I have these Maria classes that will probably get moved up. And then it's also possible that I won't be able to get through all the material on a particular subject in a night, especially when we get to some of the binary things. It just takes a long time to do it. So we'll see how it goes, and we'll keep going. All right, I don't see any questions, so I'm just going to sign out for the night. I will see you guys next week. Actually, I won't see you, but you'll see me. So we'll go again on Monday at 7.